Welcome to session 11 of Electrodynamics 2020. Today I want to finish off our discussion about electromagnetic waves by covering sections 9.4 and 9.5 in the book. So first, let's talk about electromagnetic waves inside conductors. And the discussion starts with the very simple Ohm law relating the free current density to the applied electric field. And you'll remember we had this conductivity sigma defined earlier. Now, if I replace this expression for the free current into Maxwell's equations in the presence of matter, in the presence of linear matter, then I get the following equation. So Gauss's law just becomes this in terms of the free charges that we have. This one is unchanged. This one also is unchanged. The Ampère-Maxwell relation now has the explicit expression of sigma E for the free current. And then, of course, we're using the permittivity and permeability of the matter that we're considering. Okay, so this is our starting point for the discussion. Now, we have, as usual, the continuity equation. Which, for the free charge, just means that the time differential of the free charge density with the divergence of the free current must vanish. Okay, it's just conservation of free charge. Now, if I simply replace Ohm into this, I just get that, well, maybe I'll write it down here. I get that d rho f dt, that must be equal to minus div of jf, but jf is just sigma e, so I can just write minus sigma with the now divergence of e. Okay, but by Gauss's law, this just becomes minus sigma over epsilon with rho f. So you see d dt of rho f is proportional to rho f, and that means that we can immediately write the solution that rho f as a function of time is just rho f at time 0 with an exponentially decaying behavior with a time scale of epsilon over sigma. Okay, so what that means is that in a conductor, any initial free charge, it decays on a time scale tau, which is by definition just the inverse of this factor here, epsilon over sigma. Now, for a good conductor, you're talking really stupidly short time scales here, like 10 to the minus 18, 10 to the minus 20 seconds. So, you know, very, very difficult to observe. But nonetheless, it's a finite time scale. Okay? So, because these phenomena are so rapid, we can then reconsider Maxwell's equations after this free charge has dissipated. So, Maxwell again. After the free charge has dissipated, so what do we get? Well, I mean, essentially the same equations as above, but just now that the free charge is 0. Okay, so we just get div E becomes 0, the div B was still equal to 0, the curl of E is still minus dB dt, and the curl of B was just as above, mu sigma E plus mu epsilon dE dt. Okay, so now what do we want to do? We want to do our usual trick of applying the curl on these equations. So as we've done before, so we apply the curl on, if we say 1, 2, 3, and 4, and we do that on 3 and 4. Okay, and as before, you'll remember that the curl of the curl, we can use the vector identity relating that to the Laplacian. And what we get is that we can then just separate the electric and the magnetic field. So for example, for E, what we get is that the Laplacian of the components of E is equal to mu epsilon with then the second derivative of E with respect to t. But then there's an extra linear term that comes from the one we had here, mu sigma dE dt. And similarly for B, we just get exactly the same equation for B. Okay, so these differ from the equations we had previously by the additional linear in time derivative terms that we have. Okay, but we can still look for plane wave solutions. So what we're going to do, for example, for the electric field, we're going to say that the electric field as a function of space and time is going to be some vector, E0, and then again some wave vector k that I'll give a twiddle to, dotted into R, minus omega t. Okay, I'm looking for monochromatic plane waves once again. Now, when we actually look at substitution of this exponential form in this equation here, you see immediately if I take a second space derivative, I'm just going to get k twiddle squared. Okay, and if I do a time derivative, I'm just going to get a minus I omega. So if I'm to solve this equation here for any component of E, I can just look at the factors that come out of the differentials and equate these things. So because of this one here, I get the grad square, so I will get minus k twiddle squared. So let me just put the minus sign directly. So I'd have k twiddle dotted into k twiddle, okay, and that we're just going to write as k twiddle squared. And this should be equal to then, I've got a second time derivative, minus I is minus 1. We've taken care of getting rid of minus 1. So here I have mu times epsilon times omega squared. And now this one here would have a minus I omega, but then we take care of the minus sign. So here I have a complex number, an imaginary number, I mu sigma omega. Okay, so what that means is that the k twiddle is complex. But if I choose it according to this equation, then these wave equations will be solved. So what does it mean to have a complex k? Well, it just means that as a function of displacement, I should have a non-oscillating, but really exponentially decaying factor instead. So let's write, let's just take our k twiddle to be composed of a real and imaginary part. So k plus I kappa, where k and kappa, these are just real numbers, okay? What we get if we solve this this equation here, what we get is that the k here is going to be given by the roots of this equation here. So k I'll just define as this k plus, and the kappa is going to be this k minus, and then this these combinations here, k plus or minus, just by solving the quadratic relation here, these are going to be, by definition, you see there's a scale of omega, and then mu epsilon over 2 square root, and then a big thing here with the square root of 1 plus sigma over epsilon omega to the 1/2, and this in the square root, and then plus or minus 1. Okay, so just a bit of a mess, but by simply solving the quadratic relations here, you can find these values. Okay. So what does that mean? We can rewrite our electric field as a function of r and t as our original field defining the polarization, with e to the minus kappa times r, and then e to the I k dot into r minus omega t. So what this represents is just a wave that is decaying exponentially as it propagates inside the sample. Okay, and similar for B. Okay, so for B it's the same thing. We just have to solve the third Maxwell equation, giving us the usual k over omega thing, but we'll explicit that later. Okay. So the value d, which is by definition 1 over the parameter kappa that we had here. So kappa vector is just kappa in the direction of the propagation vector that we have. So this one here is known as the skin depth. Okay, it's the distance over which the wave falls by an amplitude of a factor of e. Okay. So let's just make it a little bit explicit here. For simplicity, we're going to choose propagation along the direction z hat. Okay. So what I mean here is that we'll put the electrical field to be a function of just z and t, and this is going to be some E0 e to the minus kappa z, e to the I kz minus omega t, and the polarization is going to be chosen that the electric field is along the x-axis. Okay, so then Maxwell 3 gives us that, once again, so I'm just kind of looking at the curl of E is minus the time derivative of t, so the time derivative is going to spit out some omega, this is going to spit out some k. Getting the directions right, you just have, as usual, that the magnetic field is also transverse to both the propagation direction and the electrical field direction. This is just going to be k twiddle divided by omega E0 e to the minus kappa z, and then the same oscillating factor e to the I kz minus omega t. Now in the y hat direction. Okay, so note that there's a little subtlety as compared to before. In vacuum, we had that the electric and magnetic fields were in phase. Now, of course, the k tilde that we have here is a complex number, so you can represent it in polar form in terms of an amplitude and a phase. But the phase is going to mean that the electric field and the magnetic fields are going to be out of phase. And because the imaginary part of this K is positive, so that this is an evanescent wave, it means that there's a positive phase added to the magnetic field, which means that the magnetic field is a little bit delayed in phase as compared to the electrical field. So let's just make that explicit. Okay, so we're going to introduce polar form. So in polar form, what we're going to do is we're going to write this K twiddle as some real number times a phase. Okay, and this K here is just the big K, right? So this is maybe I'll just redo that. Okay, so this big K here is just the mod squared of our K tilde, which is K squared plus kappa squared, square root. And this thing is just omega with mu epsilon square root of 1 plus sigma over epsilon omega squared. Actually, so I'm just thinking this one here is just a squared here, like this. And then all in square root. Okay. And this phi here is just the arctan of kappa over K. Right? So so if I just look at the phases between these things, so if we set the original phase of E0 to be some value with e to the I phase delta E, and we do the same with the kind of B0 that we had here, which is this thing here. We just get that this phase difference between the two is equal to this angle here that's set by the K twiddle. Okay? So the real amplitudes for the magnetic versus the electrical field are just then K divided by omega, right? Like I have here, except that I've just kept the norm of this K twiddle in this thing. And this thing is, once again, just mu epsilon with then the big square root of 1 plus sigma over epsilon omega squared. All of this in the square root. Okay, so the final form can be written like this. We'd have that the E of Z and T is equal to this amplitude that we originally had, e to the minus kappa times z, and then the kind of physical fields are taking just the real part of the exponential phases that we had. So now I'm just going to take the cosine of kz minus omega t plus this phase delta E that we had, all of that in the x direction. And the B field is going to be this B amplitude that we had, which is K E over omega, the same form here, with the cosine of Kz minus omega t, okay? But then with a little phase shift as compared to the electrical field given by the phase of the K tilde that we had, and this in the y direction. Okay, so if we just plot this thing, then it would look like this. I'm going to put the axes like in Griffith. So this is Z. This is going to be the x direction. Okay, so E is going in this direction. And what does it mean? Well, it means that I have some some original phase in my thing. Let me put the delta E is equal to 0 just for simplicity. So the electric field is just some wave of a fixed wave vector which has an amplitude which decays as I go into the material. Okay. The B field has the same shape but in the y direction, so this is going to be y, and B is going to come this way. But the B field is a little bit delayed as compared to the E field. So if you want, the max of the curve would come here, and then this would go like this, and then also have a decaying amplitude of oscillation with a tiny phase delay as compared to the E field. Okay, if you see what I mean, right? So this is going this way, and this is going this way, right? And this is the E field, and then this is the B field. Okay, so this distance here is this phase angle phi. Okay, be careful in Griffiths, because the way he plots the electric field is incorrect. In the z direction, he plots as if the wave vector was changing as the wave penetrates. It's as if he took the wave vector to, or the wavelength here to become shorter and shorter. This is not correct. The wavelength is absolutely unchanged. So the distance between these nodes here and here is a constant. Okay, so just a little subtlety. Figure 918 in Griffiths is incorrect. Okay, but that's the way electromagnetic waves look like when they hit a metal and penetrate a little bit. And you see the distances we're talking about here are absolutely tiny because of the value of these things. Very often these things get attenuated on very, very short distances, but nonetheless there is a bit of penetration of these things in there.